Good morning, friends. I am Bharati Sagi, Assistant Professor, Department of EIE in VIGNANA JYOTHI Engineering College. So today we will be continuing our discussion we started regarding modeling of dynamic systems. We were discussing about first order systems and second order systems. In the last session, we have seen modeling second order non-interacting systems, and we will move on our discuss about interacting systems, one of very important varieties of second order systems. And this is one such variety of interacting mass balance system, wherein which we are looking at mass accumulation, and we are looking at the designing models from the conservation laws applied for mass accumulation. So again, any first order model or a second order model that we are building models, we will be using conservation laws to build transfer function models. And the wherein for these kind of systems, second order system, the governing equation is a second order differential equation. And for non-interacting system, as we discussed earlier, the subsystems, we are looking at different subsystems here. These are acting independently of one another. That is what we observed in the non-interacting systems. But coming to interacting systems, wherein which the two subsystems or two tanks that we are observing here are coupled with one another, because the elevation of arrangement of these particular tanks are done in the same elevation. Because of that, the flow rate Q1 is impacted by both H1 and H2 simultaneously. Because of this, there is a coupling effect on Q1. And therefore, as the flow rate which is linking both the subsystems is changing and continuously being influenced by both the subsystems, regulating these kind of systems becomes a difficult task, and it requires a special variety of controlling called decoupler controllers. So first we will understand how to build mathematical model for this particular type of systems, and then we will see will discuss in the later sessions how to build controllers for these kind of systems. Okay, so starting with tank 1, because this is a very important problem that keeps appearing in the examinations, almost every examinations. Interacting and non-interacting subsystem modeling is quite an important question that keep repeatedly appearing in all the examinations. So students must definitely do pay attention on building these kind of models, and it is a very simpler model to achieve, because these are tank systems, and conservation of laws for the mass balance equations would be convenient to very conveniently achieved. So starting with the tank 1, so we all should know that the starting tip to start building mathematical models is conservation law. We will recall that conservation law here. Rate of mass accumulation is equal to inflow minus outflow. This is where we begin our mathematical model for any given system. And for tank 1, we will anyway, the assumption here is the flow rate is laminar in nature. So which means the impact of H1 and over Q1 is linear in nature, which means now Q1 becomes H1 minus H2 by R1. This is the coupling effect that we are talking about, because the flow rate across these two tanks is an effect of both H1 and H2. Since we are writing the achieving the flow rate in this direction, we have to write H1 first and then H2. So the differential pressure exerted over this pipeline in this direction will be taken into consideration across the wall R1. And Q0 will be H2 by R2, right? So there is no load on the exit side of the Q0, therefore it is H2 by R2. So these two equations will be using while solving the mathematical equation for this particular tank model. So coming to tank 1, rate of accumulation is d V1 of t by dt is equal to Q in of t minus Q1 of t, where Q in is an independent variable we need to write as it is, and Q1 is a dependent variable as seen here. We will be replacing this with H1 minus H2 by R1. And fourth going, I'll be using, instead of q in of t, I'll not be using this t any further, but we'll be simply be representing with the variable itself. So this becomes a1 d h1 by dt q in minus h1 minus h2 by r1. So this becomes a1 r1 dh1 by dt is equal to r1 q input minus h1 plus h2. So we'll keep the h1 terms to the left and applying Laplace on both sides. This becomes a1 r1 s plus 1 h1 of s is equal to r1 q input of s minus h2 of s. So therefore h1 of s is equal to r1 by a1 r1 s plus 1 q input of s plus, this is plus 1 by a1 r1 s plus 1 h2 of s. So here you can observe that this h1, height of the liquid in the tank, is both affected by its input flow rate, this is manipulative variable, and also it has an impact from h2. This is called feedback impact or coupling impact. So because of this, the system behavior is different from what we have seen in the non-interacting case. So we'll be using this equation in the later case. So let us call it as equation number 1. We'll move on to the tank 2 modeling now. So moving on, we'll apply same mass balance equation for tank 2. So we already have from tank 1 this equation from tank 1 we already built, and now we move on to building for tank 2. And for tank 2, here we can see the input is q in and output is q naught, and the rate of accumulation we are finding out for h2, right? So this becomes a2 d h2 of t by dt is equal to inflow, which is q1 of t minus q naught of t, and this is q1 is nothing but, we already seen that q1 is h1 minus h2 by r1, q naught is h2 by r2. So we'll solve this one. a2 r2 r1 dh2 of t by dt, this is equal to r2 times h1 minus r2 times h2 minus r1 times h2. This becomes r2 times h1 minus, so we'll bring all the h2 terms to the left. It becomes a2 r2 r1 dh2 of t by dt plus r1 plus r2 h2 of t is equal to r2 times h1 of t. So anyway, this is again a linear differential equation. We don't have any non-linear term. Non-linear terms means either any of these dependent terms or time dependent variables has to have a higher order or some partial order, that is should have a fractional order or a higher order, then only we can say it is they are non-linear. And for non-linear systems we don't apply Laplace transformations directly, because Laplace transformations are meant for linear time invariant systems, and this is a linear time invariant system. We'll be applying Laplace. This becomes r2 h1 of s So this is the second equation we got from tank 2 modeling, and while combining 1 and 2, so we have a equation for h1 in terms of q input as well as h2, because h1 is not independently varying, it is varying with respect to q1 q input as well as h2. right? There are two variables are at a time simultaneously affecting the dynamics of H1, whereas H2 is a impact of H1. So combining 1 and 2, we'll get H2 of S by, so because our idea is to find out what is the overall plant dynamics, that is H2 with respect to the independent variable Q input of S. So that is our idea. While combining 1 and 2 and solving these, we can do that solvation. So while solving all these two together, it will give you an equation like this: R2 by A1 R1 A2 R2 into S square plus A1 R1 plus A2 R2 plus A1 R2 into S plus 1. So this is the equation we will get after solving 1 and 2, combining 1 and 2 and getting this expression for H2 by Q input. So we can observe this and compare it with the earlier non-interacting case where these two are time constants from tank 1 and tank 2. This is again tau 1, this is tau 2, and this is a coupling parameter. So S term, S coefficient has a increment by a coupling factor. So all these are positive values, area of the tanks and the restriction across the valves are positive values. Then these factors, this coefficient of S will increase for interacting case by a value A1 times R2. This is the coupling factor. Because of this additional increment in the coefficient of S, the system behaves, the oscillatory response also increases, and also the system encounters a sluggishness in the response. So it takes more time to settle down than compared to non-interacting systems. So addressing these kind of couplings is important when even the systems with more non-linearity, more noise, if the systems, these kind of systems encounter noise, then it will be more discomfort to handle these kind of systems. So care must be taken while designing controllers for these kind of interacting systems. So I hope you all understood, and these kind of mathematically modeling establishment is easy, and also mandate to before designing any controller, when you are building controllers using models, mathematical models or governing equations, this is a necessary step to start with. So thank you so much. I hope you all have understood and have a happy learning. Thank you.
Like, share, comment, and subscribe VNR Digital Learning Resource YouTube channel.